Good afternoon. How you doing? Let's try that again. I know you're back, but I haven't heard that you're back. Good afternoon. All right, welcome back. I missed you, okay? We're going into the final stretch now, the last 6 weeks, and let's see what we can do with that. This week you have lab, you talk about products and reactants. You observe, predict, and record the response of reactions in equilibrium. So you need to know equilibria and Letelier's principle, among other things, of course. All right, so and we are ahead a little bit with the lab again, because they took away 1 week from me. I'm teaching only 14 weeks this year instead of 15. So you get 1 week less of education. Aren't you sad about that, okay? And so this is difficult to arrange the labs parallel now, but I will find a way sooner or later. The last time, and many of you probably won't remember because you had this wonderful break with good weather, the last time we spoke about bond energies. If you break bonds, you need energy to break the bonds. If you formulate bonds or make bonds, you need to put in energy. So we know that there are the energy of all kinds of bonds. There are not that many bonds around. There's oxygen-oxygen, and hydrogen-hydrogen, and chlorine-chlorine, and oxygen-hydrogen, and carbon-oxygen, and nitrogen-nitrogen, and then there's a whole bunch of carbon-carbon bonds, all right? And so we have those tabulated, and we know what their average bond enthalpies are, and we can use them to calculate the enthalpy at standard state of a reaction. We usually do this by looking up the enthalpy of formation of the reactants and the enthalpy of formation of the products. We take the products minus the reactants, the sum of those enthalpies of formation, and we get the enthalpy of the reaction. But you can do this also in a way using bond enthalpies. So why do we want to do this? We can look up the enthalpy of formation. Why do we want to use bond enthalpies? If you look at biological molecules and many, many other large molecules, they only have one reactive center very often. And that reactive center, there is a change going on. There is something going on. There are bonds broken and bonds remade. So there is a reaction going on a certain part of this large molecule. So in order to calculate the energy change of that reaction, you would need all these enthalpies of formations for all these different compounds, and this is impossible because there are so many compounds that you cannot tabulate and measure and tabulate them. So what the microbiologists and molecular biologists and biochemists do, they said, okay, the rest of the molecule stays the same, but I have a couple of things there. So I got to break these bonds, and then I remake these bonds, and then I have the change in reaction, okay? So with this, they can immediately say, they do this, they break the bonds, and they make the bonds, reformulate the bonds, so this is the change of the enthalpy of that reaction, is the sum of the energy of making the bonds, of the the sum of breaking the bonds of... Okay, good, that I can regroup now. So to get this enthalpy of reaction at standard state, you take the sum of the energy of the reactants, and that means you need to break the bonds, and then you reformulate all the bonds for the product, okay? And the difference gives you the delta H. So with this, these microbiologists or biochemists, they say, okay, this is delta H is negative, so this is exothermic. Or they say, no, delta H is positive, endothermic. And with this, is a very good tool to predict the enthalpies of reaction for very large molecules. That's why you learned this. You also can use this as a tool for predicting, for example, predicting structure. And I asked you this question the last time. We have the decomposition of hydrogen peroxide to water and half a mole of oxygen. And I told you it's exothermic. What is the molecular structure of H2O2? Is it this here, or this here? Why don't you think about this? We have done this several times, I think, but I want to see if you can still remember and do the reasoning for it, and I give you 1 minute just to see where we are. Please make sure you click in. So is the structure A, B, or C? Actually, you can discuss it even. We have done this already. Just want to see if you can remember that. Because if you can solve this, you know how to use average bond enthalpies. Very good, you remember? Some of you don't remember, that's why I'm going to explain it one more time. So we have H2O2, okay? This could be this, or this. We have OH, 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 OH. So we have 2 OH bonds that we need to break. And then we make H2O that has an O and an H and an O and an H. This is also 2 OH bonds. So 2 OH on the left side, we break it, but we make 2 OH, so the energies are washed then, okay? So we can forget about the OHs. So all we have left is the oxygen. Now, we have here 1 mole of oxygen. You see that? 1 mole is in this H2O2. It's 1 mole of oxygen mixed in half a mole of oxygen molecules, okay? So if we say we're going to break this here, and this would be a double bond, okay? The double bond breaking is 497 kilojoules per mole. Let's say 500, okay? 500, and then we subtract half a mole. Half a mole is 500 half, so that's 250. 500 minus 250 is 250, okay? So this is positive. Positive. Is that endothermic or exothermic? Endothermic. But I said when I gave you the quiz, that's an exothermic reaction. So that can't be a double bond, all right? So this would be endothermic. If you have 1 mole, makes half a mole of this here, doesn't do it. Now let's see if it's single bond. Single bond, we break 1 mole of single bonds is 150, and we make half a mole of double bonds. 150 minus 500 divided by 2. 150 minus 250 is minus 100. So that's negative. Minus 100, that's exothermic. And this is what it is, and with this must be the formula. So you could forensic chemistry with bond enthalpies, okay? This was the answer. Now, we're going to talk about something totally different today. So far, we have seen that thermodynamics helps us understand all the processes in the universe. Wow, that's a big sentence. Thermodynamics helps us understand all the processes in the universe. So far, all we know about thermodynamics is that we have heat. Heat can do work. We can transfer heat in work and work in heat. Okay, we have that piston, so if we expand it, heat has to flow in to keep the temperature the same. If we compress it, heat has to flow out to keep the temperature the same, and so on. So we do work on the system, or the system does work, heat flows in, heat flows out. We have talked about this ad infinitum. And so you might have come to the conclusion that the exchange of heat, the enthalpy exchange, is our driving force for chemical reactions. You might have thought that, okay? Because we always do these exothermic reactions because they are much more fun than endothermic reactions. You have that big bang and explosions and so on. But there are also probably endothermic reactions that are spontaneous. And let's see if we can give you an example, if I can give you an example. I need 2 volunteers, please. Please, not all at once. Okay, the 2 of you, please. Yes, please. 1 here, 1 there. Please face the audience. Be safe and use your safety glasses, including myself. So I have here 2 compounds. One is called ammonium chloride, and the other one is called calcium chloride. All right. So they are solid compounds, and we say if this is our energy scale here, this is our energy scale. Yes, you're up there. Have a look there. There you are. This is our energy scale. We would be here, okay? If it would be exothermic, we would go down here. If it's endothermic, we would go up here, okay? But there are no, and so far we haven't seen any spontaneous endothermic reactions. So you're going to get this one here, and you're going to get this one, and I'm going to pour some water in there. And you're going to be my thermometer. I want you to feel the glass, if you can feel something on the glass, under the glass. Tell me what you feel, sense.
It's cold.
Yours is what?
Cold.
Cold, and yours?
Warm. Hot.
This is cold, and this is hot. So this was then exothermic, and this is endothermic. Isn't it? Hold it. This is exothermic. We started out here. But they both are spontaneous. This is not what we understood so far. We understood so far that maybe we thought when it's delta H is negative, then it happens. But it happens in both cases. So this is cold, pretty hot, huh? Be careful. And this is pretty cold. So obviously this is not the driving force. So the universe doesn't care this likes this to be in a liquid phase, and this likes to be in a liquid phase. It's the more stable phase, all right? So the universe obviously gives the energy to this one here, comes from the surrounding to dissolve that, and here this gives energy to the universe, all right? So what is it? What drives these reactions? Give your colleagues a hand, please. Thank you. So what we have is, by the way, this is a, can I have your glasses, please? Not that they're too valuable, you know. This is what happens in a heat pack. You put calcium chloride in there and water in 2 separate compartments, and then you hit it on the outside or twist it, and then it gets warm and stays warm. And this is a cold pack. You have ammonium chloride and water separated in this pack, and then you bring them together by twisting it, and then it gets cold. So we have these 2 reactions, and they both went spontaneously, all right? So what drives the reaction is the question. And this is what we're going to discuss today. So why, for example, if you have wood, and you burn wood to CO2 and water, if you put CO2 and water together, you don't make wood. All right? Or your car rusts. It goes to FeO3 or Fe2O3, iron oxide. All right? So, but why doesn't it go back, make you a new car? So it should go backwards, shouldn't it? And this is what we're going to explore today. Why does a ball, for example, roll not uphill? That's the same question. All right? And so if you have, for example, one hot object and a cold object, you bring them together, the heat never flows from the cold to the hot object. The heat always flows from the hot to the cold object. All right? So why is that? That's the question we're trying to answer. What makes chemical reactions occur? What makes them happen? And so we have a gas here, for example, and let's say that's a mole of a gas, and we have this in a compartment, and there's a valve or a stopcock, and we open that stopcock, it will distribute evenly in the two vessels. Remember when I did this bromine race, where I was trying to raise bromine, I had here a jar of bromine. Karen put that here. Then we had that long tube, and we had another jar connected to it. And of course, I never could win that race. That was evacuated, the tube, and then Karen opened the stopcock, and it was over there. Okay? And so it was evenly distributed between this here, the tube, and over there, the other vessel. So what do you think is the possibility that it goes all the way back there, and I can close the stopcock and I have the bromine in here again by itself? Is this a likely event? Very unlikely. So it has a very small probability of this occurring. It's so small that we can't even express it. Right? The most likely event is that the molecules or the atoms evenly distribute here over the whole space. All right? So the reverse never occurs. This is a spontaneous process. It says the reverse doesn't occur of a spontaneous process. All right? Chemical reactions are very often spontaneous processes. So you come here to a pressure, for example, if you have this in a vacuum here, this is a vacuum, you come to an equilibrium, a pressure equilibrium, and you have the distribution. So let's look at the work. We expand this against the vacuum. So it has to expand against the vacuum. There is no pressure to expand against, so it doesn't do any, we don't need to do any work. Okay? With this, if there's no work done, the internal energy or the energy of the gas stays the same. Yeah? The change is zero. The work is zero, and the heat exchange is zero. So why on earth does it happen? If nothing happens, why is it still happening? Why does this not stay in here and this stays empty? Because we have a new state function that we need to define. It's called the entropy. The entropy has the symbol S, is Kb, is the Boltzmann constant. It was derived by Boltzmann, times ln W. And W is it stands for a German word. It means Wahrscheinlichkeit or probability. The probability of something to happen, the probability of a distribution. So this is a statistical way to look at the entropy. So let's do that. Statistically, we look at the entropy. So we're talking about microstates. The more microstates you have, the higher your statistical distribution is. So if we look, for example, at this gas here, and we look at this gas here, okay? And so, let's say there's 1 mole in there, a statistically large number of atoms or molecules, okay? So it will be behaving absolutely perfectly statistical. So we look at this, and they have 1 temperature and 1 energy. But we know that the velocity is an average velocity. So at each time, there's 1 molecule has this one velocity, this has that velocity. And it is here and there. Now I look at another time, this has the same molecule, has a different velocity because it bumped into another one, and a different velocity in a location here. So if I look now, this was a microstate. I took a snapshot of that state, where these individual atoms were, or the individual molecules are, and this is I call 1 microstate. So I have a very large number of microstates here because they all have different velocities. Of course, we have an average velocity, and this is the Maxwell-Boltzmann distribution that I've shown you. But there's many, many possible states, microstates, that it can have. So there's a very large statistical possibility of microstates. So that means the W is very large. So with this, you could calculate your S. Now, this is all a little bit confusing. He said, what on earth is he talking about, okay? So I don't understand anything. And it's a very difficult concept. It's a very, very difficult concept, and I tried to work very hard this lecture to get this across to you. So now, if I let this expand into the vacuum, Do I have more microstates or less microstates? I have a larger volume, I have more microstates. I have many more possibilities of distributing these atoms in there or the molecules into that space. So I increase the number of microstates. Compared to this is a certain number of microstates, and this is a certain number which is larger than this one. Because now you have it all over the whole volume, and you increase the volume by a factor of 2. So let's come back to our entropy. And so this is the number of possible microstates. All right, but the entropy itself is never conserved. Energy is conserved. When the Big Bang happened, and we compare this with our energy the universe has nowadays, it's the same energy. But the entropy is not conserved. The entropy is constantly increasing. It's not a very nice picture. Actually, we're heading for total disorder and disarray and chaos. Fortunately, not in our lifetime, only a little bit. You could explain this, the increase in entropy, for example, with a dorm room, okay? At the beginning of the semester, so there were good intentions, so the books were here, and the CDs, or the MPs with 3 or whatever was there, and so the clothes was in sort of a drawer or something, and then you come midterm, second midterm, Chem 1A, the books are all over the place, there's food on the floor, there's dirty laundry, there's pages missing in the books, so the entropy has tremendously increased compared to before. Okay, so this is an increase in entropy. You have many more microstates. It's not as ordered. You take a deck of cards, for example, and you order it by color and by ascending by numbers. So, and you mix this. You will never ever, or hardly ever, you can mix as long as you will, except if you're a magician, you will never get it back in the same order. It's very unlikely, very, very unlikely. It went from a very ordered state in a disordered state. So the entropy has increased, all right? So the entropy obviously is a driving force for our chemical reaction. That is the statistical explanation of entropy. There's another explanation, and we talked about this here, when you have a warm object and a cool object, you bring them together, they will both exchange the heat, the warm goes to the cold, and then they both will have one and the same temperature. And this is the thermodynamic explanation of the change in entropy, is the reversible heat that is exchanged at a certain temperature. That's all very strange, isn't it? Okay. But this is the definition, and we will work with this. We have this definition and this definition. So let me tune you into a little bit into microstates. So you had to remember that we had this mole of gas. And that mole of gas, of course, it's the same gas, but it would be something we could number from 1 to 6 times 10 to the 23rd. It would be hard work to number each atom. But each atom behaves individually because it has a different velocity at different times. Okay? So this is why you have so many microstates. Now let's just talk about microstates. We have 6 distinguishable objects in 2 boxes. 1, 2, 3, 4, 5, 6. How many ways can you have 4 in the left box and 2 in the right box? 4. So I'm asking you, how many ways can you have 4 in the left box? 6 ways, 15 ways, or 36 ways? So you put 1, 2, 3, and 4 in the left box. Then you put 2, 3, 4, and 5 in the left box, and so on and so on. And I want to know, how many ways can you have 4 in the left box? Why don't you think about this and give me your answer, please? You can count it, actually. It's so small. Whoever had statistics here? Anybody with statistics? Good. You know the answer, don't you? Okay. Anybody has a calculator where there's a factorial button on there? I need your help. Can you look if you have a calculator with factorial button? You just can count it out, how many ways you have. Go do a factor analysis. That's a different story. I'm not expecting you to be absolutely firm in statistics, but I want to show you how this works, how one does that. This will be not part of the midterm, but it's important for you to understand the whole concept. So, since this is sort of a guessing game, I go with B, and I'm not guessing, that's the truth. And so many of you did it right. You probably counted it, or however you did it right. So, in general, the number of ways to choose R things, that would be 4 things from a group of N things, that is 6 things is. So we have N, this is the factorial, divided by R factorial, divided by N minus R factorial, okay? So what is that? What is N factorial? Is 6 divided by R is 4 things, okay? 4 factorial, 6 minus 4 is 2 factorial. You know what is this? If you calculate it on your TI 5 million, you get 15. So we are talking about moles statistical distribution. Let's just talk about 40 atoms, or 40 individual atoms. We put 20 in one bin and 20 in the other bin. So how many possible ways you have there to do that? Why don't you calculate this for me? What would that be? 40 in one bin, 40 in the next bin, so that would be 20 in one bin, 20 in the other bin. So that would be 40 factorial divided by 20 factorial divided by 40 minus 20 by 20 factorial. 40 factorial divided by 20 factorial divided by 20 factorial. Anybody? Can you calculate this for me? Anybody has a factorial button on their calculator? Please help me. I need help. Anybody? What's the exclamation mark? What is he talking about? Anybody? What are you getting there? Just give me the order of magnitude. 10 to the 11. 1.3 times 10 to the 11 or something. 10 to the 11. This is 100 billion possibilities to distribute this. Can you imagine if you have a mole to distribute? It's incredible. Absolute statistical distribution. So this gives you an idea about the number of microstates that you can have. So this is a very large number. So this, we have talked about the entropy and the change of the entropy of the universe. I said the entropy constantly increases. The entropy of the universe becomes larger and larger and larger. In the best case, it can stay, there's no change. But any spontaneous or irreversible process, which are all the processes here in our universe, if we look at the total system, they increase the entropy of the universe. So if delta S is larger than 0, you have a spontaneous and irreversible process. If it's small equals to 0, the delta S of the universe equals to 0, it's reversible and it's in equilibrium. But it will never be possible that the change of the entropy of the universe is smaller than 0. You can have a change of the entropy of the system and the change of the entropy of the surrounding, and there can be possibly something smaller than 0, but in total, this has to be larger or equal to 0. Remember that? We are heading for total chaos, like your dorm room, okay? No, only a couple of you, or nobody actually. All right. So, now let's do a little bit more statistics. And now this is our formula to calculate the entropy. Okay, statistical distribution of the entropy. So I have a process where I have 2 boxes, and I have 4 individual items here, none here. I have 3 individual items here, 1 here. So what's the probability of this? What's the probability distribution of this? And they have 2 and 2 in here. So you have to remember they have numbers on there. So you have to calculate the W for this. So, and then I'm asking you, which is accompanied by the greatest increase in entropy, delta S. If I go from state 1 to 2, or from 2 to 3, or from 3 to 1, which has the greatest increase in entropy, the greatest disorder? So why don't you think about this? Why don't you? And give me your answer, or whatever you come up with. So S is K, K is a constant times LMW. Actually, you can discuss it with each other already, because I'm not going to ask it again. Where the physicists? Are there any physicists here? Any physicists here? Nobody? Okay. Yeah, that was to be expected. Okay. The answer is actually A. But I can't expect you to do that. I just show it to you. So we have 4 individual items. There's actually only one possibility. They're all at one side. Yeah. If I have 3, there are 4 possibilities. So they are different ones. So they have a number 1, 2, 3, 4. So there are 4 possibilities to have them distributed, 3 here and 1 here. And if I have 2, 1, 2, 3, 4 different numbers, okay, so there are 6 possibilities to have 2 here and 2 here. So this is our probability is 1, 4, and 6. So what is S? S is K times ln the probability, okay? So and then we go from, let's see what we go. We go from 3 to 1, from 3 to 1. S is K times ln 1 minus K times ln 6, all right? This is minus 1.79 K. All right, this is not very large number. So delta S must be large. So then the next one, what would that be? Let's see, let's try this one. We go from 2 to 3. So this is ln 6. K times ln 6 minus K times ln 4 is this here. And if I multiply this out, it's 0.49 times K. So this is already larger than this one. This is more likely than this one here. Now the last one is K is what is it? From 1 to 2 goes from 4 to 1. So S is K times ln 4 minus K times ln 1. And this is 4 to 1. And this is 1.39 K. And with this, what was that? This is 1 to 2. 1 to 2 has the highest number. Delta S is the largest positive change. Okay, so you know how to do that. Now, let's look at the entropy of these darn piston things, okay? You know how to do this. We do an isothermal expansion and compression. So isothermal means we have a constant temperature. The temperature of that gas will not change. Yeah? It's constant. With this, delta H equals 0. And we know that delta H is Q plus W. If I set this 0, Q equals minus the work. All right? Q is minus the work. So we have an isothermal expansion. If Q is minus the work, so if I do an expansion, the gas does work. Okay? So that's negative. All right? So to stay the same temperature, heat has to flow in the system. isothermal. The gas does work, loses energy. Now heat has to flow in to replenish that energy with heat. And with this, Q is larger than 0, so it flows in. Now I'm asking you, I have an isothermal expansion. Delta S, my system is this here. So if I look at this is my entropy before, and this is my entropy of the system after. Did the entropy increase of the system or did it decrease? It increased, exactly, because it was written there also, but it increases because now you have double the volume. You get more states, more microstates. So delta S of the system is larger than 0, okay? So if I do the opposite, I do the compression, so I do work on the gas, okay? Work on the gas, work is positive or equal to 0. So now I'm increasing the internal energy of the gas. I did work on it, the energy increased, but I don't want the temperature to increase, so I have to let the heat flow out. So that means Q is smaller than 0. That would be the compression. Did I talk about compression or did I say expansion? Compression, okay. So I do work on it here, that's positive. Heat has to flow out, Q is negative. And with now, what is the entropy change of the system? Before I had this here, and now I have this here. Did the entropy change? Did it get smaller or larger? Smaller. I have a smaller volume, exactly. The smaller, so the entropy of the system is smaller than 0. So something must happen with the entropy of the surrounding because delta S of the universe is system plus surrounding. And the change in the surrounding has to be equal or larger than the change in the system in order to be larger than 0. Okay? So we come to this in a second. Let me ask you a question. We have an ideal gas and it expands isothermally against the vacuum. What is the delta S of the surrounding? So that's the surrounding. I'm not talking about the system, I'm talking about the surrounding. I already alluded to it actually in my comment before. So why don't you think about this and give me your answer? So we expanded isothermally against a vacuum. What is delta S of the surrounding? Still hot? Very cold. That's how can you cool your beer. Put a little salt in there. That's what you do. You put salt in water, same thing. Okay, you need some help. So why don't you think about the changes that you do to the surrounding? If you do an isothermal expansion against the vacuum, just look at this and see if there's anything going in or out from the surrounding. And then think about it again. Why don't you discuss this with each other and see if you can come up. What happens to the surrounding? Is there any change or is there no change? For the entropy to change, there has to be something happening to the surrounding. If nothing happens, there's no change. So what's the answer? I go with B. Don't get fooled. Just look at your system first. Does anything happen to your system? No, exactly. So you have an isothermal expansion against the vacuum. So the external pressure is 0, okay? So you expand against the vacuum. Do you do any work? No. Does the energy change? No. So isothermal means delta E is 0. That means work is minus the heat. And now what is the work? The system does not know work because it expands against an outside pressure of 0. That means that the work is minus the external pressure times delta V, and this is 0, so this is 0. With this, the work is 0 and Q is 0. So there's nothing happening in that system. So there's no change, and there's no change. There's a change in entropy because we have now a larger volume. The entropy changed. The delta S of the system became larger than 0, but the surrounding, no change was there. All right? So, and I say delta S of the universe is delta S of the system that was larger than 0, plus delta S of the surrounding that was 0. That gives you delta S of the universe is larger than 0. Okay? This is definitely a reaction that can happen. All right, so that was the answer. Now let's go to another one, because it's so much fun. Now, we have a gas that is isothermally compressed. Now I want to know, what is delta S of the surrounding? So I compress it isothermally. So you need to look at this. What flows in, what flows out? Is there anything that flows in or out? So what is delta S of the surrounding? Is it smaller than 0, equal to 0, or larger than 0? So just compress that gas isothermally. And then see what happens to your surroundings. Where's Robert? I don't see him in the back here. You pointing at me? At Robert? No? Where's Robert? In the back there. Maybe I forgot his name. It was Robert, wasn't it? Or was it Eric? So what is delta S of the surrounding? That's the question. So what happened to the delta S of the system? That's the first question. Not for me to totally get ecstatic, but it is right. The surrounding, the entropy increases. Okay? So why is that? So let's first look at the system itself. okay? So the entropy of, we have isothermally compressed. So we do work, I'm looking at the system, not what this question is referred to, just at the system. We compressed it isothermally. So we compress it, we do work on the system, the energy of the system goes up, okay? Delta H increases, or delta E increases, okay? So, but I want it isothermally, so heat has to flow out, all right? Heat flows out. With this, I probably say that I have less microstates, so the delta S of the system was smaller than 0. We did that, okay? Delta S of the system was smaller than 0. But now heat flows into the surrounding. What does this do to the entropy of the surrounding? It increases it. Of course, they have higher velocity. Now they have more microstates, these molecules in the surrounding, whatever the surrounding is. So with this, you have the delta S of the system. I said it's smaller than 0. The delta S of the universe is delta F of the system plus delta S of the surrounding. It has larger than 0. Even without thinking of the heat, I have to say, for this to happen, I have to say that the surrounding has to be larger than 0 because I have to have that number larger than 0. That's another possibility. Look at it. But the delta S of the surrounding, because heat is flowing into the surrounding, is larger than 0. Okay. I think that's it for today. And I see you on Wednesday.